Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So for the last talk of the afternoon, we'll have Brian Bertsch. First, I wanted to say a little about my own interaction with Oliver Atkin, which certainly wasn't as extensive as Brian's or Winnie's or Dan's. But I first met Oliver in 1974, probably exactly the same time Winnie did, when I was a graduate student at Harvard, when he visited there. But I didn't really have that much interaction with him until about 15 years later, in the summer, I think, of 1989. I came into my possession, by a means I really don't remember, a Xerox of many pages of computer output that Oliver had produced, along with some scribbled annotations of some of his ideas, written in a rather terse but suggestive style. But knowing how much insight he had, I tried to pay attention to it, and in fact, I spent probably a week poring over it until I understood his ideas, and then I had some ideas, and I found his email, wrote him an email. This was probably July or August, and I didn't hear from him for about a week. And then I got an email saying, well, you've reached me during the summer, and I have a rule that I'm going to take a sabbatical from mathematics during the summer. So, however, what you've written interested me so much that I'll break my own rules. So I guess in retrospect I should feel very flattered. So he and I then spent the next month or two exchanging emails with some of my ideas, and I had actually come up with pretty much the same ideas. It seems that Noam Elkies had also been in possession of this manuscript, but wasn't in communication with Atkins. And Noam basically came to the same conclusions I did, and just as I was finishing writing my things up, I received Noam's manuscript, who had actually done that and a little more. So at that point, I just put the manuscript back in the drawer. But my interaction with Oliver was actually quite interesting and pleasant. And then 4 years later, when I started where I work now, Oliver spent the summer with us at our summer program, and well, I can't talk about what we worked on there, but it was very interesting. And in any case, here's Brian Bertsch to speak more about Oliver.
Yeah, well, first I should thank the organizers for inviting me. And then a matter of whiteboard technique. Is that, from the back row, is that about the right size? Okay. Yes, and this will be much more a biographical talk than a mathematical lecture. So I won't really be using the blackboard very much seriously. And as a general guide, if I write something on the middle of the board, it's an aid to people who can't hear what I'm saying otherwise. But if I write it at one end or the other, it's probably something I want to keep. So the middle of the board will probably look a horrible mess and will get rubbed out fairly frequently. Okay, now, which bits of Oliver's work and life am I going to talk about? There's rather a lot of it, so I'll have to keep to the earlier parts, I think. I think his life, for the purposes of this talk at any rate, can be divided into about 6 sections. My writing is fairly bad. (1925 to 2008). Well, the first 20 years, 1925 to 1945, called education. The next few years are 45 to 61, early research, 61 to 70, Atlas, 70 to 72, I think I'd better call crisis. People may know why I say that. 72 to 85, Renaissance, after the crisis, and 85 to 2008. There exists elliptic curve cryptography, which means in this context that in particular René and Victor have said quite a lot about Oliver's work in that period, and certainly know more about it than I do. So I'll probably stop there. Now, in more detail, I'm in print, or more exactly on net, as having said quite a lot about that period. And I suspect quite a lot of people here have read it, because I think of everything I've ever written, it appears to be the thing which has been read most. And here, Francois and Dan have said a certain amount, so I may not say all that much there. So I'll concentrate on this part, which has the advantage that I'm probably the only one in the room who knows all that much about Oliver's early years. In 1961, he wasn't, that's not all that early. Okay, his education until he was about 20 years old was really quite extraordinary. A very, very hothouse upbringing for a young mathematician. He went to boarding school, age 9. Then when he was 11, he got a scholarship to Winchester, and he was in Winchester age 12, that would be 1937 to 1942, I think. Now, I should explain that Winchester is the oldest school in Britain and probably the most academic. Really, by modern standards, in all this time, it was really quite odd. The scholars lived apart from the other students. They lived together in a very beautiful medieval building called College. It was very beautiful. It was probably Tudor. It was extremely cold in winter. And they all lived together in the strong sense that there was no privacy. They worked in the same room during the day, and they slept in a dormitory upstairs at night. Oliver was pretty bright, possibly even bright by the standards of Winchester. However, he wasn't nearly as bright as 1 or 2 years ahead. There was a little group of mathematicians, including Freeman Dyson and 3 others who became fellows of the Royal Society. That's to say, academicians. That was a strong year. Anyway, Oliver probably enjoyed this very rather extraordinary environment. As you know, there was a war on. So university admissions were sort of odd. And I think in 1942 to 44, he went to Cambridge, age 17 to 19. And Cambridge at the time was a little odd because all the young lecturers had been conscripted into the army, or if they were unfit in some way, they had been conscripted into some essential wartime work. So that the people teaching tended to be extremely distinguished and decidedly elderly. Besikovich, Littlewood, very fine, but not young. And at that time, there'd been no opportunity to revise the syllabus on modern lines, so probably what was taught was very classical analysis, applied mathematics, only epsilon algebra. Okay? So Oliver probably would not have learned much algebra in Cambridge. On the other hand, the classical analysis would probably including elliptic and modular functions. Not that much of them, but he probably would know what they were as a student. Okay. What happened next? Well, he graduated in 1944, and 1944, he was posted to Bletchley Park. Well, in Britain, Bletchley Park is considered to be where computing began. And I think from really, anyone would agree it was the first major computing project which really made a difference to people. It was important. When he got to Bletchley Park, he was posted to a small group called the Newmanry. This was a small group, I would say a small research group of about 28 strong mathematicians. And while most of Bletchley Park was engaged directly in the business of decoding German, or possibly Japanese, but usually German, signals which had been intercepted, the most important ones being the naval ones. The duty of the small research group was to maintain the capability to decode of those of the operational people, so that in particular, if there was a German naval code uncracked. Crack it. Now, of course, in this essential task, they weren't alone, because the operational people were pretty bright too, and even if one's job was actually decoding all the messages, you could get pretty good at decoding other codes you hadn't seen before. Okay. Oh, and I should have said about 28 strong mathematicians, and they were plus about 200 wrens. The point is that a wren is a member of the Women's Royal Naval Service. Girls who volunteered for the armed service were screened. The brighter, reliable ones tended to be posted to the wrens, and the brightest and most reliable tended to be sent to Bletchley. And in Bletchley, there were several thousand wrens who did data processing. They're essentially the input and output system. Okay, who were these mathematicians? Well, I'll write down the names of some of them. You won't know them, but let's see. There was Henry Whitehead. I should have started off with Max Newman, who was in charge. Sean Wiley, who was assistant director. Others included Peter Hilton, Sandy Green, and others. The ones, I'm not going to write down 28, the ones I've written down were people I got to know myself afterwards. A remarkable thing that no one working at Bletchley has ever talked to me about Bletchley. Security really was secure. Now, the particular people I've named are he was my professor in Manchester. He was a topologist, pretty stern sort of guy. Henry Whitehead was a topologist, founded topology in Oxford essentially. Peter Hilton and Sean Wiley, they were algebraic topologists, come algebraists, wrote a nice book together afterwards. Sandy Green, excellent algebraist, actually my senior colleague. From Oliver's point of view, it probably cured his lack of algebra because these guys would have talked about commutative algebra and vector spaces and that sort of thing is purely, as part of their thinking process. So we've got to go around that. There's also the point that actually you don't have to be an analyst or a number theorist to be good at decoding, apparently. And of course, I should have said that Turing was very much the most important member of the group. He wasn't strictly a member of the group because he was too important. I mean, you wouldn't have had Newman as Turing's boss. That would be idiotic. On the other hand, for this sort of job, he was fairly essential. Okay, so Oliver was there, working there for a year. it's very difficult to think of a more exciting mathematical environment. It's also true that the mathematicians Oliver knew fairly well, Freeman Dyson, Turing, others, or actually a class or two above those who were never lucky enough to work with afterwards. Okay. So, by the time he was 20, Oliver certainly knew what mathematics was about. And to some extent, one could argue that anything which came out of that was just a little bit tame. And indeed, the next few years were, by contrast, fairly routine. Let's see, 1945, end of war, but Oliver, he still had 2 years national service to go. So he went to the National Physical Lab and thought about aircraft wings. I can't imagine that he enjoyed it. Then, in 1947 to 1952, he was a research student in Cambridge. And that must have been pretty good, because by 1947, the war had sort of worn off, and all the people like Peter Hilton and Sean Wiley, who ought to have been teaching him when he was taking an undergraduate degree in 42 to 44, and who really did teach him when he was in Bletchley, all of them were back in Cambridge, and a lot of other bright people. And he did research under Littlewood on partitions. And then in 1952, he got his doctorate, and 1952 to he went to Durham as a lecturer. And now I'll talk about his thesis at the end of the paragraph, as it were. 1952, he went up to Durham as a lecturer, and well, he's written a few decent papers. Durham, it's a lovely little town, small town, completely dominated by a cathedral on a little hill in the middle of the river, in the middle of the town. Very beautiful. The important thing about the cathedral for Oliver was it had an organ. He was a fine musician, and he played the organ. And then in, let's see, 1959. He got married, and, well, many people would have just stayed there for life, but not if you'd had that sort of start up the age of 40. He was going to get restless. Now, so he only lasted in Durham until 1961. Now, what did he do his research on? Well, time for some mathematics, and time for some notation. He did research on partitions, so let's just remind ourselves Pn is the partition function. It's got a generating function. I'll call it f of q is sigma 1 to infinity Pn q to the n, which of course is going to be the product from 1 to infinity, 1 minus x to the n inverse, which is a very satisfactory way of defining the partition function. And this is really, inverted commas, a modular form, because if we write q to the 1/24th product 1 minus q to the n, where q is, Winnie wrote some very convenient notation for me. Q is e to the 2 pi I z. If e to z is that, then everyone knows Jacobi's identity, that this is sum from minus infinity to infinity minus 1 to the n, q to the 6n, let's get it right, 6n plus 1 over 2, 6n plus 1 squared over 24. That is right. And this, and then comparing that with that, f of q, I think, is q to the 1/24th times eta inverse. Okay. And then this is eta itself is a modular form because it's a theta function. It's a modular form of weight a half. With a multiplier, I'm not going to write down the functional equation. It's quite complicated as a modular form. Everyone knows and loves it because delta of z is eta of z to the 24th. F itself is also a modular form apart from the 24th root of q. It's a very nasty modular form because it's weight minus a half, which is dangerous. However, being a glutton for punishment or obstinate, Oliver did research on the coefficients of this rather perverse modular form eta of q. Okay? The partition function, a terrible function. Yes. Now, I'll come to his... yes. Well, I'm here. There's a conjecture by Ramanujan. I hope I get it right. If 24n minus 1 is congruent to 0 modulo 2 to the a, 3 to the b, 5 to the a, 7 to the b, 11 to the c, then p of n is congruent to 0 modulo 5 to the a, 7 to the beta, 11 to the c. What actually Ramanujan conjectured had a b where the beta is, but that was wrong, and beta is 1 or 2 when b is 1 or 2, but after that it only grows half as fast. Okay, so that's Ramanujan's conjecture, and this was proved for the 5 to the a, 7 to the b by Watson in, I'm not sure of the date, I'll say 1938, which is probably right, and for 11 to the 1 and 11 to the 2 by Morris Newman. I think. It may have been Joe Lehner, but I'm pretty certain it was Morris Newman. And Oliver's problem, his thesis problem, was complete the job. And of course he did. But first, Oliver's first paper was rather nice. First paper, joint with Swims and Dyer. There's a conjecture by Dyson. You may thinking of Oliver's, it was a bit early for a conjecture by Dyson. In fact, this conjecture was conjectured by Dyson when he was still at school and published in Eureka, which was the Cambridge Students' magazine, but it wasn't trivial. Here, a particular case, I think, says that the partition function for things of the form 5n plus 4 is always congruent to 0 modulo 5, and partition function for things of the form 7n plus 5 is also congruent to 0 modulo 7. Okay? But there's particular cases of that. And Dyson's conjecture said that if pi is a partition, define the rank of pi equals mod largest bit minus the number of bits. So if you partition something with 7 plus 6 plus 2 plus 1, the rank is going to be that 7 minus the number of parts, which is 4, so you get 3. And then if n is congruent to 4 mod 5, sort partitions modulo n into classes according to rank, modulo 5, and then classes all the same size. So this gives you a simple combinatorial reason why the number of partitions of 4 or 9 or 14 is divisible by 5. The theorem itself, the proof of this is as proved by Oliver and Peter Swinton Dyer. They had to reinvent Ramanujan mock theta functions. It was a tour de force which absolutely delighted Dyson, but completely non-trivial. And then the same is true mutatis mutandis for mod 7 OK2. 11 didn't work. All right. So that's Dyson's conjecture and Oliver's first paper. About 40 years later, a guy called, I think, Garvan produced a different invariant of partitions, not the rank. Well, actually, it was used a different variant of partitions, which Dyson had called the crank, and proved a similar theorem for 11 using the crank instead of the rank. Okay. Now, where were we? Oliver went on, and I think his third paper was called Proof of Conjecture of Ramanujan. And in a sense, that was more routine. Whereas to prove this thing, they'd had to use infernal ingenuity. To prove the Ramanujan conjecture, Oliver essentially followed the path followed by Watson and Morris Newman, which was to manipulate modular equations involving various special modular functions to prove an identity to prove a congruence for the coefficients of a particular rather difficult modular form. And really, the extra ingredient Oliver needed was simply knowing more about modular functions and forms than anyone else, and loving it. Okay? So he'd written a thesis, and he was doing good work on what I'd call a rather narrow area, which he loved. He'd got a good job in a nice place. He'd got a new wife. Why wasn't he happy? Well, it's obvious. I mean, he'd been in Bletchley. He knew what real mathematics was about. He knew he could do more. Also, looking at modular functions, he felt that though there's nothing as simple to be proved about the partition function, no obvious divisibility properties, he felt there must be congruence properties and so on available. And I'll put something up which I'll call Oliver's idea, because the way I'm putting it up is much too sloppy to be called a conjecture, and it's probably about what he was thinking at the time. So let f of z equals sigma 1 to infinity an q to the n be modular form or function, not necessarily of positive weight, in fact probably not of positive weight, and but vanishing at I infinity and invariant by a congruence group, and n equals q to the k probably. Then there should be a congruence like to replace the Hecker relation, which my notation is not actually the same as Winnie's, but A P n plus p to the k minus 1 a n over p equals a p a n yes, satisfied by new forms. And let's just write the same thing down. And just replace the equality by a congruence modulo the level. Now, as I've written it down, it's too sloppy to be right because new forms aren't necessarily rational. So I should say there should be congruences like, and you should probably say that the coefficients you've got are a linear combination of things which satisfy an identity like that. Or alternatively, you could ask for a relation with longer terms. So you have to to get a correct sensible statement, you've got to modify that. But this is it's his idea, it's not. And I don't think he ever did formulate it absolutely right. Now, the trouble was that he had this idea, and he was interested in modular forms, horrible modular forms, like e through z inverse, weights minus a half, or he got a bit more modest in his thoughts and settled for the J function, which is a nice function of level 1. And I should say that a good example for the sort of thing in the theorem is going to be J of z over n plus J of z plus n minus 1 over n, or this with coefficients nth roots of unity. And then that qualifies as one of those, and this can be read off as a congruence relation between the coefficients of the J function. And he did a little bit of hand computation, which suggested this might well be so. But as everyone can see, the coefficients of the J function are far too large for hand computation to be of any use. And in 1961, Atlas Fellowship advertised. The duties of the Atlas Fellowship would be to work on one of the world's largest computers at the time, and essentially do what he liked so long as he worked hard. Well, he thought about this question, which it's a good idea, but completely uncheckable without heavy computing resources. I've no doubt he remembered Bletchley and thought that mathematics is more exciting than Durham. And so of course he applied, and of course he was appointed. I think they jumped at him. So 1961 he moved down to Atlas. Well, at Atlas, excuse me while I check that I'm throwing away the correct pages. At Atlas, he was in his element. He could work as hard as he liked, which was pretty hard. On the whole, he got on pretty well with other people, though those who didn't really enjoy it when he walked down the corridor singing Wagner fortissimo, but that was okay. And, well, he worked. Mainly computing modular forms, lots of modular forms, checking out this sort of thing, computing other things as well. It's well known that for a while the check that the engineers did on the Atlas computer at the beginning of the day was to compute the first page full of coefficients of e to the z raised to the 25th power. and make sure it was always right. It's a good test for a computer if it's got things like vowels, which can be a little bit rickety. And well, I arrived in Oxford, I think it was 1964, and at that time I needed to learn about modular forms because Shimura had told me that there were elliptic curves which were parameterized by modular functions, and I wanted to know about them and see if the conjecture was right. But at the time, the literature on modular functions was perfectly horrible. There were lots and lots and lots of modular forms, all running about, connected by lovely relations, and the literature was completely unsystematic, and there are a lot of beautiful theorems known about them, but the trouble is it was extremely difficult to find out from the literature whether a useful fact that was known to be true was something which someone had actually proved, or was the sort of folklore that no one ever got round to checking. So, and there was Oliver, so I asked him, and he put me right. What I can't quite understand was that the Atkin-Lehner paper wasn't actually published until 1970, and the things which Oliver told me about 4 or 5 years earlier appeared to be straight out of Atkin-Lehner, as I remember them. But I think that's partly publication lag and partly Atkin and Lehner getting round to the effort of writing it up. Anyway, as Winnie's already said, that was it wasn't a difficult paper, it wasn't a terribly new paper, but it completely transformed the theory and made it easy for everyone to use. It was ever such an important paper, in fact. Then, well, I'd better keep things short, because if I finish early, everyone will be very happy. And if I finish late, everyone will certainly be unhappy. What else did he do as Atlas? Well, he yes, there was his one of the best known things is his lovely essay on feasible computation, which I hope is compulsory reading for everyone who does computational number theory. If anyone hasn't read it, they'd better go and read it. It's easily available on the web. He was generally helpful. There are a couple of things I mentioned in my 1995 talk, where he did just extremely helpful computations. In particular, there's a conjecture due to Tate, which is was called the Bertsch-Tate conjecture because I supplied him with the result of some computations, and should have been called the Atkin-Tate conjecture after the guy who did most of the computation. I had done some of them, but yeah, that was the non-congruence group paper. The biggest thing he did at Atlas, really, it was what he planned to do, which was computations relating to this idea. And the trouble there is that it's a very general idea. There are an awful lot of cases one can check by looking at a computer. They all come out right. Proving a single case is actually rather difficult. So Oliver, let's see, 1968, there was a paper essentially on the coefficients of J of Z on those lines, which checked the idea for powers of primes up to 37, which showed fairly decisively that it was basically right. But going up to 37, there was only about one case where the coefficient stopped being rational. So that it was precise. I think the conjecture, the idea was what he proved up to 37, except in one case, was, I think, just as I've written it. But for p equals 29, he had to get it right. Except p equals 29 needed the adjustment due to the space which sort of wasn't there being two-dimensional instead of one-dimensional. And then in a paper with 1967 with O'Brien, the ditto for e to z inverse, i.e. congruences for p of n modulo, I think 5 and certainly 13 and probably 7. Even though there's not a divisibility theorem for 5 except for the residue 4, but the congruence is modulo powers of 5 otherwise. So that, I think, summarizes what he accomplished at Atlas, more or less. Now, unhappily, all good things have an end. 1970, he left Atlas. More or less at the same time, let's say 1968 to 1972, there was a complete revolution in theory of modular forms, which was more or less summarized at the 1972 Antwerp conference, after which the theory of modular forms became a matter of representations as described in the as everyone thinks them nowadays. But of course, before it wasn't like that. So there's, I'll say, advent of representation theory, and also advent of p-adic modular forms. Now, in a sense, this was for Oliver a success, because Sayre recognized that the modular function is the prototype of a non-obvious p-adic modular form. Well, I suppose it's the prototype of a whole covey of p-adic modular forms, because when you take these congruence conditions, you get a different setup for each prime, so that the J function gives rise to a family of not particularly closely related p-adic modular forms. And that, in a sense, made sense of that. On the other hand, it was a bit of a disaster, because I don't think Oliver's background in algebra was ever that good. And having his beloved subject turned into representation theory and p-adic hoo-ha, well, the p-adic stuff was all right, but I don't think he ever liked the representation theory. So, and the other disaster from that point of view is that representation theory is very dependent on geometry. And to get some geometry out of a modular form, you've got to have some geometric object, and you associate a geometric object with a modular form of positive weight, Cougar variety or what have you, and you can take modules and represent the Galois group as acting on the tape module and all that jazz. But if you take a form of negative weight, it's horrible. So on the one hand, that was dead right, and on the other hand, hardly anyone's ever talked about a modular form of negative weight since. Much more disastrously, when Oliver resigned from Atlas, he'd taken a job in Arizona, and almost immediately after he got there, his wife died. So he was in a foreign country with children aged 7 and 10, by all accounts very nice, sensible children, but even so. And he somehow had to manage. His job in Arizona lasted 1 year, and then he went to Brown for 1 year, and actually my imagination boggles. But then, where's that? In 1972, he went to let's see, he went to Chicago Circle, University of Illinois at Chicago. Yes, the standard initials are UIC, which at lunchtime, Willie didn't describe it as being a particularly nice place, but he went to Chicago Circle and found a little house in the village of Oak Park, and apparently the folks at Oak Park took this mad Englishman to their hearts, and he stayed there for the rest of his life very happily. So that was 1972. He at last got settled. I'd lost contact completely, and so most people who knew him, but still, from 1972 he was okay. And which brings me to this period. Well, because of the revolution in the theory of modular functions, he changed his interests. He remained knowing everything about classical modular forms and modular functions, but for a little while there wasn't any evidence that he was working on them. Because, well, he was always, even when he was at Atlas, quite reluctant to write a paper unless someone else wrote it for him. So it's, though the harder one tries, the more one finds, it's actually quite difficult to find what he was doing during that period. And for instance, he was doing quite a lot. Let's see. He was 1972 to 5, I think. He was Duncan Boole was his student. Wrote a very nice thesis. I think that must have been Oliver algorithm for composition of quadratic forms. In Henri Cohen's book, there's he refers to Oliver as the author of such an algorithm. I think it must have been that period because that's the sort of thing that Duncan was working on. Then a little bit later, work with Winnie Lee. Well, that was modular forms again. Classical. 1976, there was a conference always known as Antwerp 2 at Bonn. And he was certainly there. I can remember because he certainly made inquiries about which is the best organ in Boyle. Boyle is the bit of Bonn, the other side of the river, which was where the Max Planck Institute was in those days, and he found the best organ, and he played at it, and from what I remember, he seemed pretty well. But I didn't talk to him very much because I was talking to other people, and Nelson Stevens was computing something. Well, I never. 1980. he was working with Jimmy Mackay, producing the moonshine conjecture came out in 1978, and got proved by Bertsch in 1982, I think. And in between, there's various verification work done, and Oliver joined with Mackay and someone else producing a moonshine module, whatever that may be. His interests transferred very much to primes rather than modular forms. So of course we never forgot about modular forms. Francois. Then they've talked about that. Then finally, in 1985, excuse me, I bought a pot. In 1985, René's thesis, what is it? René School's thesis reads him, Oliver, René deliberately not tried to optimize things, because I don't think he really thought that it was a practical algorithm, but Oliver, he looked at this and he thought, this is where I can use my lovely modular forms. So he rushed into it and immediately produced an algorithm which was practical for decently large primes, not large by present-day standards, but bigger than one could do by hand. And then Elkis came along and got us. Anyway, at that stage, he thought I ought to hear about it, so I got an email from him, and from then on, I was back on his mailing list, and it was a great pleasure to receive emails from Oliver, either directly or via Victor's net, on the net, and that's about the time for me to stop, because from then on, everyone else knows more about Oliver than I do.